Hey guys, we're back with the second part of the notes for 8.5. Most of what is on here is already going to be written, so I'm definitely going to allow you to pause the screen, write what you see. Perfect. Okay, so we are going to talk through most of this, but I don't necessarily need you to be like working or solving a problem. This is more like just information part of the notes, okay? All right, so the first thing, what's the pattern for a function if it's a polynomial? So we've seen quadratic. We know that's ax squared plus bx plus c. We've seen cubic. But the problem is you would never really know how many letters are needed if you didn't know what the degree is, right? So if it's squared, I need 3 letters because I'm going to have a squared, a regular x, and a constant. If it's cubic, I'm going to have 4 letters. So if we don't know in general, we use a sub n, and that n is going to match your degree. It's going to match your highest exponent. So our next term would be a sub n minus 1, meaning it's 1 less than that value because my degree is going to drop down 1. So for instance, if I was going to write this out, let's say we were doing something to the 8th power, then we would have a sub 8 x to the 8th power plus a sub 7, 7, x to the 7th plus a sub 6. See how I just drop it down? The sub should always match whatever your exponent is, okay? Not super important, but I do want you to understand that that's our base here, okay? All right, second thing, how do we know if it's a polynomial to start with? Well, the exponents have to be whole numbers. They have to be positive. You are not allowed to have radicals or rational exponents, okay? Second, you have to have coefficients that are real numbers. So I can't have anything that's an imaginary number. I can't have a complex number. I can't have something like, I don't know, anything that would be imaginary, okay? So let's go down to this next part. And let's go through a couple of these to talk about why they are a polynomial or why they are not. So I'm going to scroll up just a little bit. If you want to pause the screen first, that's fine, but we're going to fill in some things. All right, so I am looking at this top section right here. It says, decide whether the function's a polynomial. If it is, write the function in standard form. So for instance, on number 1 and number 3 and number 4, all of those have positive exponents, okay, positive whole numbers for their exponents. All of them have real numbers for their coefficients. So fractions are fine, whole numbers are fine, negative numbers are fine. The only issue is some of them aren't in the right order. So like on number 3, I had to put my x squared before my x, before my constant. On number 4, I had to put my 1/4 x to the 4th at the beginning. He has the highest degree, but then it has to be a countdown. So then I need to the 3rd power, to the 2nd power, to the 1st power, and then my constant. Okay, so I just reordered those. The reason number 2 is not a polynomial is because the exponent is a variable. So we absolutely know this function. It's an exponential function. It's just not a polynomial, okay? All right, let's go down to the next part. So I am moving to here. So on this one, we're going to go through 3 different pieces. We're going to do the degree. Remember, that's the highest exponent in the problem. Let's do that one first. So my degree right here, highest exponent is a 2. My degree on this one is I lied. It's in the wrong order, but this one's degree is a 4, highest exponent. On number 2, my degree is a 1 because my highest exponent is on this x. And then on number 4, my degree is a 3, highest exponent. When I do my type, that is the name of the type of problem with that degree. So in this case, on number 1, quadratic, because it has an exponent of 2. On number 2, we would call that linear, because it has degree 1. On problem 3, it would be quartic, because it has a degree of 4. And then on number 4, because it has degree 3, we call that cubic. And you should have seen all of this earlier in notes, okay? All right, last thing I want to hit on this part is the leading coefficient. You'll just see it as LC a lot of times. But the trick is leading coefficient doesn't mean the very first number in the problem. So it doesn't mean the 7 and the 1 and the 3/4 and the 2, okay? That's not your leading coefficient. It means the number, the coefficient that's in front of the variable that holds your degree. So on this one, we do get to use 2. Because he is on the x squared and my degree is 2. But if I look at problem 2, my leading coefficient's actually a -3 because the -3 is with the x. On problem 3, my leading coefficient is the 2 because he's on the x to the 4th. And on problem 4, my leading coefficient is 7 because he's on the x to the 3rd. It has to be the coefficient that's on your degree term, okay? All right, last part, we are going to move down to here. All right, all of these are no's. I want to focus on the why, like tell me why it's not. So on problem 1, you are not allowed to have integers or negative numbers, integers for exponents. So you can't have can't have negative exponents. Okay. When it comes to this guy, we cannot have rational. Let me back that up. Can't have pi or radicals as our variables, because remember, square root 3 really means 3 to the 1/2 power. Can't have that. And finally, on this last one, we cannot have variables as exponents. Okay. All right, if you need to pause the screen, copy anything down that we just wrote, go ahead. Otherwise, we're going to the next page. All right, and similar idea, I am going to have you kind of pause the screen, copy what you see, and then we'll talk through it. We're going to do the top, and then we'll do the bottom part, okay? Perfect. Okay, so on number 2, it says the graph of every polynomial is smooth and continuous. That means it has to be a smooth running curve. It can't be janky like this, okay? It has to be smooth and continuous and flow between all of the points. We will have what's called turning points, and this is a rule you're going to have memorized. So the maximum number of turning points, that's how many times the graph changes directions, is always 1 less than degree. So if you think about it, a quadratic, an x squared, changes directions 1 time. Something that is cubic changes directions twice. So I follow it, goes up, turns down, turns up. If I did something to the 4th power, and we're just assuming it's positive, it's going to change from down to up, back to down, back to up. Now, does it always have that many turning points? No, that's the maximum that it can have, okay? So it's not always, but it's the maximum number of turning points. When we talk about number 3, we're going back to that odd or even. You've already watched part of the video on this guy as far as what in behavior does. So if the in behavior is opposite directions, it's an odd function. If the in behavior is going the same direction, then it's even. So I like to kind of think through these with my hands a lot of times, and I'll put my thumbs together and say, all right, is it even? They're both going up, positive, going down, negative. Or I'll put my thumbs together and say, all right, so they're going opposite directions. My right hand leads. If my right hand goes up, it's positive. If I switch them and my right hand goes down, left hand up, that's negative. Okay. All right, so that should be kind of a review. This is the big part. So if you would, pause the screen, copy what you see. Wonderful. Okay, so tangent and double root are the 2 vocab words I need you to know here. If you end up with a part of a graph, like your polynomial graph, is tangent to the x-axis, that's this. It's kind of like saying it bounces off the x-axis. You're saying it touches it, but it does not cross it. It bounces off of the line. And it could be doing that from the bottom, or it could be doing that from the top. Okay? Get that out of there. Boom, boom, boom. Okay? That is called a double root. What it means is the multiplicity or the exponent, you're using that root or that factor or that 0. You're using it twice. Okay? So if I have a double root of x minus 2 and x minus 2, then I'm not going to cross at positive 2. I'm just going to touch 2 and turn right back around. So if I was going to write out the factors for this problem, I would have an x plus 1, right? Because that's minus 1. I would have an x minus 1, right? Because that's plus 1. And then I would have x minus 2 squared. Or I could say x minus 2 twice. Okay. We would see that there's 4 x's here. Based on the shape, it makes sense because that's to the 4th power, right? That's basically what we're coming up with. Okay, so these are things that you're going to have to recognize out of an equation so you know the rules when you're graphing without a calculator. Okay. All right, we talked about what the degree could tell you. It tells you how many different times you're going to cross the x-axis, so how many solutions you have. Remember that you might have imaginary and you might have real. We'll talk about that in a second. But it also tells you the max number of turns. You just need to remember that it's 1 less. So if I have let me use green real quick. If I have a cubic, then I have 3 solutions and max of 2 turns. Okay, if I change that to a quartic, remember quartic is 4, then I would have 4 solutions. Again, they might be x-axis intercepts, they might be real numbers, they might be imaginary, but I would have a maximum of 3 turns. Again, maximum does not mean it turns that many times. It just means it could turn that many times. Okay. All right, final part I want to go over is what it means to be imaginary and real on the graph. So every time your graph crosses or is tangent to the x-axis, that means there's a real root. You have a real 0 or a real root there. Now, any other roots that you have to have, like if you know there's 4, but it only touches once, then that means you have 3 imaginaries. You don't have to write that down. I'm just giving you an example. So for instance, on this first, if I kind of look through these, this guy is x to the 3rd. Okay, so he's cubic, but he only touches 1 time. That means he must have 2 other imaginary roots. This one is x to the 3rd also. He must have 3 roots. 1, 2, 3. All of those are on the x-axis, so they're all real roots. On this one, he's x to the 4th. You can tell that based on his direction. So that means he must have 4 solutions, but he does not cross the x-axis at all. That means all 4 must be imaginary. Okay, so we're just counting up how many you would have. Finally, is it possible for a polynomial to have 1 complex 0? All right, in order to answer this question, we have to remember what complex means and what 0 means. Complex is anytime you have an answer like this, a plus bi. It has an imaginary number as part of it. 0 means that you're talking about a place that is a root or a solution that crosses on the x-axis. So is it possible to have a complex point on the x-axis? And the answer to this would be a no. Let me fill that in real quick. The answer to this would be no, because there are no imaginary numbers on the x-axis. So you might have complex solutions, but you can't have a complex 0 because it wouldn't be on the x-axis then. Okay. All right. If you need to pause it, copy anything down. That is the end of our second video. We do have one more video for 8.5.